So the way we compute the spectral evolution operators was to compute the trace. And that was defined as starting at some point, evolving for time t, ending at some point. But in case of trace, the initial and final point have to be the same. That's generalization of matrix trace to functionless continuous indices. And then we integrated all initial points over our full state space. But now we have a new formula. I'm supposed to integrate only over the fundamental domain. I'm supposed to start in fundamental domain, use my symmetry-reduced law, and in that case I end up in fundamental domain. But we are acting on a vector space, which is dimension of number of the tiles. So we also have to take the trace of the vector part of this, and that we show there was a regular representation. The element H, which if you remember had a property that if I started at X, I use my full state space lower evolution, I end up at Y by definition. But if I started in fundamental domain, then Y could be written as H operation, saying that the image of the initial point on the full evolution ends up on some image of the final point. No. So in this trace formula, what this means is that that will only work if H equals identity. Because we have shown that for regular representation, the only non-vanishing trace is the identity trace. So, nothing interesting has happened. It just says that if periodic orbit is periodic on the full space, in other words, H is identity, it's also periodic on the fundamental domain. So it's the same trace formula as before, it's just that we integrate over smaller, we integrate over a single tile, but we take care of correct integration for the full space by taking this trace. So you say, what the heck, what is this all good for? Now comes the brilliant thing, which takes a couple weeks to explain, so we'll see how Oliver does, because he'll explain the next step. This is a reducible representation. This is not an irreducible representation of the group. So Frobenius and Schur tell you that this can be written, it can be diagonalized and by similarity transformation. And once you have done the similarity transformation, it will have format 1, 1. And then in case of dihedral group on 3 elements or permutation on 6 elements, irreducible representation of dimension 2 will show up twice. And now what happens is that when we rewrite the trace as a sum of these traces, then it turns out that while the whole trace is 0 for every group element, the sum of these 4 traces, individually they actually give you non-vanishing contributions. And they'll give you non-vanishing contributions whenever the orbit is a relative periodic orbit, meaning that its image ends in another tile at the same location, just group translated. And that will show up in these things. So the big deal is that this trace of this particular regular representation, notice this is just intrinsic to the group. So everything that happens is just intrinsic to the group, doesn't care in which application you're using it. Trace of regular representation of any group element which is co-character, just that's the word, particular representation. So that's called regular of group G. That's actually sum of traces alpha goes 1. And these ones are non-vanishing, can be non-vanishing also, group element not equal identity. So trace formula, once your symmetry reduction suddenly becomes sum of trace formulas. Everything is computed fundamental domain, and they'll have beautiful interpretation. So we have learned how to interpret one of them already in a billion examples. So in a billion examples, we saw that we always looked at most symmetric representation. So we had some function rho. There was a rho that in spectroscopic notation has label A1. Don't ask why. Defined on fundamental domain, which was the sum, all group operations of the group, averaged by the order of the group, of the function only computed on fundamental domain, but multiplied by the group element. So that's an obvious thing. You just average as much as you can over your function. You take all of its copies. Original function is different on different parts of the state space. You bring them all together, you add them up, and average, you get a smoother function. So that's called symmetric, fully symmetric representation. It turns out that in physics, in quantum mechanics, this always has to do with the ground state, lowest energies of some system, and in ergodics, theory has to do with natural measure, the most natural state that dynamics brings you to. In statistical mechanics, it's also a ground state. And then it's very easy to also find a function called antisymmetric, and that one is done over odd permutations, or meaning odd number of transpositions. They give you a character -1. So that generalizes what you learn about antisymmetric representation. But now it turns out when groups are non-abelian, you get higher dimensional representation, you get their repeats. And I don't know a very quick way to explain how this works. So we'll have to spend another lecture on that.